No matter which direction we look in or how far away our telescopes and instruments are capable of seeing, the universe appears pretty much the same on large cosmic scales. The number of galaxies, the types of galaxies that are present, the populations of stars that exist within them, the densities of normal matter and dark matter, and even the temperature of the radiation that we see are all uniform independent of the direction we look in. On the grandest cosmic scales of all, on scales of several billions of cubic light years, the average difference between any two regions is merely 0.003%. The biggest differences that we see, in fact, aren't a function of which direction we look in, but rather how far away we're looking. The farther away we look, the farther back in time we're viewing the universe. And the greater the amount, the light from those distant objects is shifted towards longer wavelengths. A lot of people, upon hearing this, get a particular picture in their heads. The greater the amount the light is shifted, the faster these objects are moving away from us. Therefore, if you look in all directions and reconstruct, at what point in space would we see all directions receding equally? You could locate the center of the universe, and we can perform that exercise if we like, but the center of the universe isn't what we arrive at. Most of us understand intuitively that when objects move towards you, the waves they emit appear compressed, with their crests and troughs closer together. Similarly, when they move away from you, the waves appear the opposite of compressed, rarefied, with their crests and troughs farther apart than if they were stationary. Although we typically experience this with sounds, as you can tell whether a fire truck, a police car, or the ice cream cart is moving towards you or away from you dependent on its pitch, it's true for any wave, including light. We refer to this motion-based shift of the waves as the Doppler effect, named after its discoverer. Only when it comes to light, a change in the wavelength doesn't correspond to higher or lower pitches, but higher or lower energies. For light, longer wavelengths mean lower frequencies, lower energies, and redder colors, while shorter wavelengths mean higher frequencies, higher energies, and bluer colors. For any individual object that we measure, because of the nature of matter in the universe, there will be atoms and ions present that we recognize. All atoms and ions emit and/or absorb light only at particular wavelengths. If we can identify which atoms are present and we can measure a systematic shift to these spectral lines, we can calculate just how red-shifted or blue-shifted the light actually is. What we find when we do this is something quite remarkable. For the closest objects, we see both red shifts and blue shifts corresponding to speeds ranging from a few hundred to a few thousand kilometers per second. Galaxies like the Milky Way, which aren't tightly bound to large, massive groups or clusters of galaxies, typically top out with lower speeds, while galaxies near the center of large, massive clusters can achieve speeds as high as approximately 1/2% the speed of light. While the first scenario is easy to understand, objects exist in space and move through it, the second one requires a little bit of explanation. In Einstein's general relativity, space isn't simply a static background that particles and other objects move through, but rather it's part of a fabric, along with time, that evolves dependent on the matter and energy present within it. A large mass in one particular location will cause that fabric to curve around that location, compelling every quantum in that space to travel not in a straight line, but rather along a path determined by the curvature of space. The bending of starlight around the sun during a total solar eclipse, for example, was the first definitive test that showed gravity obeys Einstein's predictions, in conflict with those of Newton's older theory of universal gravitation. Another thing that general relativity dictates is that if you have a universe that's uniformly filled with matter and/or energy, that universe cannot maintain a space-time that's static and unchanging. All such solutions are immediately unstable, and your universe must either expand or contract. So how do we know how big this ball of dough is, where we are located within it, and where its center is? This would only be an answerable question if we could see beyond the edge of the dough, which we cannot. Imagine a loaf of raisin bread rising in the oven. The dough expands uniformly, and each raisin moves away from every other raisin. To any raisin, it appears as though it is at the center of the expansion, but in reality there is no central raisin. In fact, to the extreme limits of the part of the universe that we can observe, the universe is still perfectly uniform to within that same 1 part in 30,000 everywhere. Our Big Bang, which occurred 13.8 billion years ago, means that we can see out to a maximum of about 46 billion light years in all directions, and even at that distant limit, it's still remarkably uniform. This places no constraints on how large the ball of dough that represents our universe can be, how large the unobservable universe beyond our visibility limit is, what the topology and connectedness of the unobservable universe is, and what the allowable shapes for the limits of our universe are. This includes the sub-questions of whether our universe even has a center or not, whether it's finite or not, and what our location is with respect to any larger structure the universe may have. All we can conclude is that the universe appears perfectly consistent with general relativity, and that just like any individual raisin within the dough that couldn't see beyond the edge of the dough itself, any observer could lay equal claim to the obvious but incorrect conclusion you'd draw if you saw everything moving away from you. I'm at or very near to the actual exact center. But there's a crucial point we need to clarify. It's not correct to say we're at the center at all. The only thing that's privileged about our location in space is that the objects we see nearby are the oldest, most evolved objects we can see today, with the more distant objects being younger. The expansion rate nearby is lower at present than the expansion rate we see at greater distances, and the light from the closest objects is less redshifted, and their shifts are less dominated by the cosmological component of redshift than the more distant objects. This is because the objects that exist throughout the universe can send no signals that travel faster than light. The light we're observing from them today corresponds to the light that's arriving right now, but must have been emitted some time ago. When we look back through space, we're also looking back through time, seeing objects as they were in the past, when they were younger and closer in time to the Big Bang. Back then, the universe was hotter, denser, and expanding more rapidly. For that light to arrive at our eyes, it had to get stretched to longer wavelengths over the entirety of its journey. There is, however, one thing we can look at if we wanted to know where, from our perspective, all directions truly appeared as perfectly uniform as possible. The cosmic microwave background, which itself is the leftover radiation from the Big Bang. At all locations in space, we see a uniform bath of radiation at precisely 2.7255 K. There are variations in that temperature depending on which direction we look, on the order of a few tens to perhaps a few hundred microkelvin, corresponding to those 1 part in 30,000 imperfections. But we also see that one direction looks a little bit hotter than the opposite direction, what we observe as a dipole in the cosmic microwave background radiation. What could cause this dipole, which is actually quite large? About plus minus 3.4 millikelvin, or about 1 part in 800. The simplest explanation is, going all the way back to the beginning of our discussion, our actual motion through the universe. There actually is a rest frame to the universe if you're willing to consider we're close to the right speed for our location, but we're a little bit off. This dipole anisotropy corresponds to a speed, or a peculiar velocity, of about 368 plus minus 2 kilometers per s. If we either boosted ourselves by that precise speed, or kept our current motion but moved our position to be about 17 million light years away, we'd actually appear to be at a point that was indistinguishable from a naive definition of the universe's center at rest with respect to the overall observed cosmological expansion. In essence, the center of the universe is an illusion, a perspective that changes depending on where you stand and how you move. After all, we can see for some 46.1 billion light years in all directions, and 17 million light years is only 0.037% of the radius of the universe away from us. But the more sober truth is not that we're near the center, but that any observer in any galaxy would conclude that they were at or very near the center as well. No matter where in the universe you're located, you'll find yourself existing at this particular moment in time, a certain finite amount of time after the Big Bang. Everything that you see appears as it was when the light from it was emitted, with the arriving light being shifted by both the relative motions of what you're observing with respect to you and also the expansion of the universe. Depending on where you lived, you might see a dipole in your cosmic microwave background corresponding to a motion of hundreds or even thousands of kmms in a particular direction. But once you accounted for that piece of the puzzle, you'd have a universe that looked just like it does from our perspective. Uniform on the largest scales in all directions. The universe is centered on us in the sense that the amount of time that's passed since the Big Bang and the distances that we can observe out to are finite. The part of the universe we can access is likely only a small component of what actually exists out there. The universe could be large, it could loop back on itself, or it could be infinite. We do not know. What we are certain of is that the universe is expanding, the radiation traveling through it is getting stretched to longer wavelengths, it's getting less dense, and that more distant objects appear as they were in the past. It's a profound question to ask where the center of the universe is, but the actual answer, that there is no center, is perhaps the most profound conclusion of all.